interactions, and we're going to talk about surface energy melting and wetting. And the only announcement I have, as you may have seen via the C-Tools email, is that homework 2 is up online and it's due 2 weeks from today. So the problems from homework 2 cover the topics on interactions, and it'll, like the last homework, I wanted to let it out early so you could get started, but a lot of the stuff hasn't been covered yet. There is one problem on fluid flow, there's one problem on melting. You'll be able to do the melting problem after today. And then there are a couple problems that deal with balances of surface forces and electrostatic forces. And you'll be able to do parts of those, but not all of those quite yet. Okay. So last time we talked about intermolecular and surface forces and built this idea that because of the way the atomic structure, the structure of atoms interact with each other, you get intermolecular forces. And we saw there are many types of interactions and induced dipole interactions, dipole-dipole interactions, electrostatic interactions, bonding interactions. And we kind of focused on one generalized type of interactions that lead to attractive forces between molecules and therefore by summation lead to attractive forces between small bodies. So things at the nanoscale that we consider like nanoparticles, nanotubes, and nanowires. We define sort of the range of these interactions as about 1 to 100 nanometers. So beyond the length at which bonds would feel each other. So remember we talked about the ideal case of breaking a material when you stretch the bond by 10% of its bond length. So that's way beneath 1 nanometer. But now when we're beyond bonding, even if we have two unbonded solids close to each other, they're going to feel each other because of these interactions. We took the simple approach of calculating total energies and then taking the derivative to calculate a force between two bodies by summing these pairwise interaction potentials. So you'll remember we had the idea of one atom or one molecule sitting out in space and facing a big semi-infinite surface and kind of feeling that surface one atom at a time. And we built that based on a potential law just being inversely proportional to the separation distance between the atom and the surface. And for van der Waals forces, which are widely applicable and kind of lump a bunch of different types of interactions together, we used the Lennard-Jones potential, which looks like this. And for the attractive forces, we take the 1 over r to the 6th portion that is in our length scale range that is beyond the equilibrium separation. And in practice, we saw some examples, and we'll see many more throughout the semester, how van der Waals forces practically govern adhesion, local deformation, and assembly. A lot of things govern assembly of nanostructures, but one thing that gives attraction and can be screened or can be enhanced is the van der Waals forces that can lead to assembly of things into things like bundles and lattices and so on. And we also saw from simulation and some practical examples how these forces can be strong enough to deform structures. So in the case of single-wall nanotubes that, this is maybe about a 2 diameter nanotube, you can get some deformation, some squashing of it, and there's no extra pressure or there's no applied force on the top, but rather it's the atoms of the substrate feeling the atoms of the tube and pulling down on them. And that can have a very practical consequence, sometimes a benefit for things like adhesion and sometimes a consequence for things like processing, for removing nanotubes from a substrate or for debundling them, for example, for separation, as we'll see later on as well. And this idea of summing individual interactions into body interactions ended up in a table that lets us, for example, knowing the math behind it, then calculate the total interaction energies between, for example, two spheres of different radii and a sphere and a surface and two cylinders and so on. And one of the important takeaway points from last time is that the power on the distance between the two gets lower as the dimensionality of the bodies changes, or the dimensionality of the bodies gets bigger. So because you're integrating over many things, we go from, say, a 1 over r to the 6th for the case of two atoms or two molecules having this interaction to a 1 over the separation in the case of two spheres. And we can see how these also build up and indicate that the length scale of the interaction gets bigger as the dimensionality of the body gets changes. So 1 over r to the 6th drops up much more quickly than a 1 over a different power, a smaller power, in the case of solid bodies like so. And I'm sure many of you have read this paper, which discusses some of the relevance of these interaction forces and adhesion forces in organisms in nature, and has in fact found that a lot of things that are small can do things like climb walls and rely on these different types of adhesion between their feet and surfaces. And we closed saying how it's found that the number of contact points, or the number of little toes between these organisms and between surfaces, increases as their body mass increases, because you need to be able to create more adhesion force with a solid surface. And the paper touches very briefly on how the mechanics of supporting the weight is derived from a balance between the van der Waals forces, the adhesion forces, and the elastic stiffness of these contacts. And by idealizing each toe as a hemisphere, you can use classical theory of contact mechanics to calculate the force that would cause a certain deformation of the tip here. And then you can imagine balancing that force with the adhesion force, and there's a certain limit, for example, how far or how much you're going to indent the tip of the toe given a certain strength of interaction. And you can imagine as that indentation happens, then the contact area changes and some atoms get closer and pull a bit more, and there is an equilibrium. And this also defines the force that's necessary to pull it off, and that therefore defines the force that it can support if it's an ideal case. And there are a lot more interesting practical aspects in terms of the real geometry of these structures. You note that they're not necessarily these hemispherical tips, and have maybe an angled tip like so, and this can relate to how the creature walks, or for example what forces the creature needs to apply to unstick its toes to be able to take another step. Because it could, imagine you had a great adhesive that it could support 10 times its body weight, but that's no use if it can't figure out how to unstick its toes to take up and move to the next step. So there's been a lot of work in engineering nanostructures to create these kinds of adhesives, and we won't go through the detailed mechanics of these structures, but for example, essentially trying to mimic the end of a gecko's foot. So this is an SEM image of the actual setae on the foot of a gecko, and here are some SEM images of researchers who made pillars of vertically aligned carbon nanotubes to try to understand how to mimic those mechanics. So the idea is that each one of these little pillars, which contains a whole bunch of nanotubes, behaves kind of like a compliant toe of a gecko's foot. And this is just a summary of the results that are described in this paper. And here they're measuring the shear force necessary to peel a particular area of what they're called the gecko tape here, or their synthetic surface meant to mimic a gecko. And the particular insight that this paper put forward is that the dimensions of these patterns, the effective synthetic toes, govern how much adhesion you get. And for example, if you make an unpatterned surface, basically where you just have a full area film of nanotubes, you might locally get strong adhesion, but because you can't deform the individual pillars to adapt to roughness in the surface, you don't get nearly as much adhesion as you do if you pattern the surfaces. And they have different results for different heights and widths of the pillars. And there's also, this is just one example of a whole lot of work. There's also work, for example, using polymer structures and, for example, studying the geometry of the tip, whether it's planar, whether it's spherical, symmetric, or asymmetric. And here you can begin to think about, it grabbing and then pulling and lifting it up to peel it off to take another step. And if this is something you're interested in, there's certainly a lot of literature you can read about. And one of the kind of practical aims of this is, you could say, well, to make new types of dry tapes, so tapes that don't damage surfaces, can hold large amounts of weight. And also there's a lot of work in small-scale robots making things like little micro insects, or even robotic creatures that are about the size of something like a gecko. And the idea is that these robots could climb walls and do things that regular robots couldn't do by employing these kinds of adhesives on their toes. And there are some examples of little robots that people have made, or little vehicles that actually can climb up surfaces, and that's pretty cool. Okay, so that's a recap of last time, and today we're going to talk about surface energy and melting and wetting, and it's a bit of an extension to what we talked about last time, in that we're trying to build this picture of because nanostructures have so many atoms at the surface, what is special about their properties, and what then about those surface atoms governs the interaction between and among bodies of nanostructures. So we'll go through a definition of surface energy and work of adhesion, and then we're going to use that to build a simple thermodynamic model of the melting point decrease of a nanoparticle. And the idea is that because a nanoparticle has a lot of surface, free surface is essentially unsatisfied bonds, then it melts at a temperature that's significantly below that of a bulk. And you need to get to pretty small nanoparticles, but you can have, for example, a nanoparticle of gold or of iron that melts at, say, 60 or 70%, or maybe even less, the melting temperature of the bulk material. So that has a lot of practical implications for processing these structures, because you know that if you look at only the bulk melting point, then you'd assume it's solid, but because of this suppression, the materials are actually liquid, and the atoms are a lot more mobile and fluid. And then we'll see that this idea, which we're going to develop for a spherical particle, can be generalized to some different geometries with a bit broader generalization, but just taking into consideration whether you have a sphere or a wire or a plate, a thin film. And then we'll talk at the end a bit about the design of surfaces to control wetting behavior. For example, how another idea of biomimicry is to, for example, understand why certain plant leaves don't like water, like the lotus leaf, for example, where water drops bubble up and also roll off very easily. And that has led to some inspiration for designing synthetic nanostructures to mimic those behaviors. And for readings, I have 3 papers up online. 2 talk about melting of nanostructures. One is quite an old paper talking about this simple theory of size dependence of melting temperature of particles. And then the Goldstein paper is a more experimental paper that has some nice observations of these effects using transmission electron microscopy. And then there's a paper by Tuteja that talks about designing of surfaces for superhydrophobicity and superoleophobicity, so surfaces that repel water and surfaces that repel oil, which has been a recent innovation of this group's work, in that it's typically harder to get surfaces to repel oil than repel water because oils have lower surface energies. And we'll learn why that's true at the end of the lecture today. Okay, so the first piece we'll need for today is I just want to go through a definition of what we'll call surface energy. Because you've probably heard of surface energy in context of wetting and things like contact angle, and it turns out it's very close to the definition we derived last time to calculate the energy due to van der Waals forces. So basically what I want to do is go from the picture we developed last time, where we built up this pairwise interaction for one surface facing another surface, and now say if we had say one surface or one body just by itself, what do we call its surface energy, or what energetic value do we give for how it will interact when it comes close to another surface, and how can we use that to, for example, get an idea of the melting behavior. So the way we'll do this is just let's consider, for example, if we have our 2 surfaces where we have, say, 2 blocks of atoms facing each other, and I'll draw these simpler and more quickly to save time, and say we have a separation between them of distance d, and we define some characteristic length of the one of the surfaces as d naught, and we'll define that more precisely in a minute. So what I want to do is define the kind of total energy of this system. And we're going to call this total energy big W, and we're going to have 3 terms. We're going to have a first term, which we'll just say is a large constant, which we're not going to calculate, but we have to say it's there first. And this represents what we'll call the bulk cohesive energy. Basically the interactions between the atoms in one side and all the other atoms in total around it. And then we'll have a second term, which will represent the energy of the unsatisfied bonds on the surface and you can see that these are of opposite signs because we sort of have to take a little bit away due to the unsatisfied bonds on the surface from what we're calling the bulk cohesive energy. And then we'll have another term which we're going to give a negative sign, or ends up being a negative sign from last time, to characterize the interaction between one surface and the other surface. And then this is what we calculated last time as the van der Waals energy. So if we neglect the bulk energy, because that's kind of fixed and isn't going to change when we change the separation between the surfaces, we can write that this total energy is just the energy of the unsatisfied bonds and the van der Waals energy, which we can say is equal to A over 12 pi times 1 over our special length scale d naught. Imagine just considering the energy if you had a small separation here, basically what's missing by not having atoms here, and then the expression for the van der Waals energy we had from last time, which is just the Hamaker constant, divided by 12 pi times 1 over our main separation, capital D. And so now if we collect like terms, we can rearrange this to say that we have A over 12 pi d naught squared times 1 minus d naught squared divided by d squared. And this is all per unit area, because this came from us taking a unit area of the solid last time. So now if we consider the case where the separation D is much larger than our small length scale, d naught, then this term drops out. So we just have W is equal to A divided by 12 pi times d naught squared. And this is what we're going to define as twice the surface energy. Because we have two surfaces here, and if we consider the energy of one surface by itself, we need to divide this quantity by 2. So we can view this parameter gamma, the surface energy, as the energy we need to take a solid and to separate it into 2 halves. Question?
The D naught length scale for both materials is the same.
Yeah. And we're going to relate it in a second to the atomic spacing in the lattice. So we haven't defined D naught yet. And so what happens is if we consider the arrangement of the atoms in the lattice, if we consider a simple lattice where we have, say, atoms spaced by a distance we'll call sigma, then we would come up with a result that's discussed in Israel-Ashvili, that gamma is equal to A divided by 24 pi times sigma divided by 2.5 squared. And sigma is just the lattice parameter of a solid. So we're assuming we have a lattice defined by one lattice parameter, but the reading goes on to discuss that this is a pretty good approximation for most solids except for metals, and says that you can relate the Hamaker constant to the surface energy by this relationship and get pretty accurate results within 10 or 20%. And the main exception to this is the case of metals, because metals have more free electrons, and because of the way they're bonded, the surface energies of metals are typically higher than they are in the case of solids, where we're only assuming this van der Waals attraction.
I have a question. What's the difference between D naught then and sigma?
It's just defined as sigma. Well, what the reading does is it boils it down to sigma divided by 2.5. So I was using a D naught just to be able to draw a parallelism to our simple separation model. And it's a characteristic dimension of the lattice due to the interaction between the atoms. So we can just note that the surface energies of metals are typically much, much higher. So now I want to define one more term that we'll call the work of adhesion, and we'll call this as the energy required to create two free surfaces. So basically, to do what I said a moment ago, to take, say, two halves of material or one piece of a solid material and decide where you want an interface and break it and separate it into two pieces. And in terms of notation, we'll say that the work of adhesion is equal to twice the surface energy gamma. Essentially, you need to apply this amount of energy to separate a surface into two unit areas. And you know, in principle here, we're really saying we're going from contact to infinity, so infinite separation, and this is all occurring in vacuum because we're not thinking about the material in between. But clearly, if there's a medium here, then the way that the medium interacts with the surfaces can affect how much energy is needed to separate them, whether the medium likes the surfaces or doesn't like the surfaces, for example. But now let's think about what happens if we have two different materials, or we want to understand how to get a picture of the surface energy between two different materials. So if we want to, for example, think about what the surface energy between two different materials or two identical surfaces made of different materials is, so we'll call this gamma 1, 2, then we can visualize this as, say, taking a block of material 1 and separating it and creating two surfaces of material 1, and then taking a block of material 2 and creating two surfaces of material 2, and then pairing a 1 and a 2 up with each other. So if we continue with this kind of additive model, we can say that we need to create one unit surface of 1, create a unit surface of 2, and we need to connect 1 and 2. And in terms of our nomenclature, this would be equal to 1/2 of 1, 2, 1, or 1/2 of 2, 1, 2. So it's like having a case like this for here, and gamma 1, 2 would be the energy of the surface, the interface between 1 and 2. So two things important from what we just did is, one, kind of getting a picture of what the surface energy means in the context of the attractive potentials we talked about last time. So, and then getting an idea that we can imagine an interface between two different materials as kind of building that up from a process, an additive process of taking the same material, breaking it apart, and putting those two dissimilar materials together. And we'll just need these two pieces to build the model of melting and surface stability that we'll talk about now. And just as a little aside, you can, for each solid on the periodic table, you have a surface energy that can be calculated or can be measured. And it turns out that as you go across the periodic table, as you go across in rows, the surface energy goes up in a periodic fashion. Basically, as the bonding configuration of solids gets more stable, the surface energy increases. And there's also a pretty consistent correlation between surface energy and melting temperature, which makes sense because as a solid is more stable, then you're going to need to apply more energy to melt it, and therefore it's going to melt or transition from a solid to a liquid phase at a higher temperature. And so the smaller fluctuations here and what causes them are beyond our scope, but generally there's a correlation between the stability of a solid and its melting temperature. And that analogy can also be applied to small structures, because if you have a lot of surface and surface is less stable, then that can affect the melting temperature of a small solid. And relatively how stable or unstable that surface is for a particle of a particular size, and what the particular bonding characteristics of the material inside the solid are, affect the specific melting point of a nanoparticle of a certain material and a certain size. So what we're going to do is we're going to develop a very simple model that has a bunch of assumptions to consider the temperature at which a small sphere of material would melt. And before we start doing the math, I want to mention 4 specific assumptions we're going to make. We're going to assume that we're starting with a spherical particle, so it's always round. And we'll assume that the melting of the particle begins at the surface of the solid, and there's a uniform layer of liquid around the surface. So the model is going to have this thin liquid shell, and then in practice, when we compare this to experiment, we're not really going to think about where the melting happens or what the liquid thickness is at a particular time, but this is going to let us derive a stability criterion. Basically, when the net free energy of the system decreases by melting, then we'll know that it's energetically favorable for the particle to melt at a particular temperature. And we're going to assume that there are no volume or density changes as this process occurs, although the density of a liquid would be slightly different than the density of a solid. And we're also going to assume that this particle is floating, so there are no surrounding effects. As you can imagine, and we'll see later, it might be different if the particle is sitting on a substrate and like the atoms of the substrate are grabbing the particle and having some interaction, or if it's surrounded, say, in another solid or another liquid. That would change the relative surface energies and therefore change the temperature at which the particle melts. But we can get a first-level picture just by considering it to be spherical and unconstrained. Okay. So now we're going to call the solid state 1, and we're going to call the molten state, or this semi-imaginary state where we have this little layer of liquid around, as state number 2. And so using the definition of small r as the radius of the particle and T as the thickness of the liquid layer, let's get started. So the first thing we're going to do is we're going to calculate the free energy change that happens to the particle as melting occurs. So we're going to use what's called the Gibbs free energy, and the generic definition of the Gibbs free energy is the maximum mechanical work that can be extracted from a system without volume change or heat transfer. And a formal definition would say that the differential in Gibbs free energy G is equal to the volume times change in pressure minus the entropy times the change in temperature plus a summation based on adding and subtracting material to the system. And we're going to assume that there's no pressure change and there's no change in what's in the system. So we just have that our change in free energy is equal to minus small s times the change in temperature. And we'll come back to this in a minute. And then we're going to define that the total change in free energy of our little particle system when melting occurs, so delta in big G at melting, is equal to the change in free energy of the bulk plus the change in free energy of the surface. So what we're going to do is we're going to first calculate delta G bulk, and then we're going to calculate delta G surface, and then we're going to add them up, and then we're going to define this stability criterion and say what is special when melting happens. So then first for delta G bulk, we want to go define the difference between the second state and the first state, so the molten state or the liquid layer state and the solid state. And in the second state, we have a volume of liquid, V little v sub L, times some specific free energy per unit volume of that liquid. And we have some volume of solid, Vs, times G sub S. And then we subtract the first case, where everything is solid, and our V is V sub T, which is just the total volume of the sphere. So because we know the liquid layer thickness in the second state is T, we'll be able to figure these out as a function of R and T, but we won't do this quite yet. So we can say this is just equal to VL GL plus VS GS minus VL plus VS, because the volume doesn't change. So VL plus VS equals VT times G sub S. And then the VS GS will cancel. As you can see, this will cancel with that. So now we just have that, I'll come back down here, delta G bulk is equal to the volume of liquid in the second state times delta G, or GL minus GS. And to define what delta G is, we're going to go back to our definition of the Gibbs free energy and relate it to the entropy and to the temperature. So by our previous definition, we said that dG dt at constant pressure is equal to minus the entropy, so this is the entropy per unit volume. So then we can integrate, and we can say that delta G is equal to an integral between a couple of limits we'll define in a moment of this minus s dt, assuming that for each phase S of t is constant. And if we want to define some limits here, let's define the limits as the bulk melting point, so the temperature at which the bulk solid melts, which we'll call T sub mb, and a temperature T, which will be the temperature that we're operating at. We're going to end up solving for this T, and this T is going to be the point at the temperature at which the nanoparticle melts. So when I say assume that S of t is constant for each phase, what I mean is that for a liquid, we have a value S for the liquid, and for a solid, I have a value S for the solid. So then this just becomes a simple subtraction. The S pops out, and so for the liquid, we can say that delta G of the liquid is just minus the entropy of the liquid times T minus T and B, and the same thing for the solid. So now delta G is just equal to the change for the liquid minus the change for the solid, which is equal to SL minus SS times the temperature difference. And this quantity, the difference in entropy between the liquid and the solid state, is typically defined as the latent heat of melting basically how much energy needs to go in per unit volume to melt the solid, divided by the temperature being the bulk melting point. So we can relate this change in entropy per unit volume for the phase transition to, at our level, what we can look up as a bulk property of the solid based on its and its bulk melting point. So now we can say that our small delta G is equal to our latent heat divided by the bulk melting point multiplied by the difference between these two temperatures. This is basically like a free energy difference, because we're considering that the particle may melt at a temperature different than the bulk melting temperature. And we're going to now add this to the surface contribution, because if we have surface and we have a change in surface energy because there's so much surface on the particle and the surface is important, then basically that relative instability of the surface is going to pull the bulk melting point down, and there's kind of this phenomenological exchange between surface energy and bulk energy. And well, like basically based on how much free energy change occurs, favorable change occurs due to melting because of the surfaces, that can kind of pull the bulk melting point down by equaling with this energy change we are deriving here. So now, just to complete our total free energy change for the bulk, we just had that as being the volume of the liquid times our change in free energy, which now we can say is equal to this quantity which is just the volume of our spherical shell of liquid with a thickness of t. Just r cubed minus r minus t cubed. So this is kind of our part one. And we'll save this for now. And now we'll start to look at the surfaces. So now we want to find the change in free energy due to the surface. So if we imagine going from the case of a solid to the case of a liquid and a solid, then in the context of surface energy, like we were talking before, we start out and we have a surface with energy gamma S, and we end up and we have a surface with energy gamma L, and we have a surface with energy gamma SL. So we could say we have to like destroy this surface, and we have to create these two surfaces. So we're just going to say that like destroying this surface is subtracting its energy, and creating the surfaces is creating the equivalent energy of that surface. So now we can say that delta G of the surface is just these surface energies multiplied by the relevant areas, and we just add those up. So if we want to create these two surfaces, we have the surface area of the sphere of radius r times gamma for the liquid surface which we create, and then we have the surface area of the inner sphere times gamma of the solid-liquid interface which we create, and then we have the surface area of the sphere times the solid surface, and that's minus because we destroy the surface. And of course, as we said before, there are no volume changes, so we know that the volume of the initial one is equal to the volume of the final one. And then if we collect like terms here, we have 4 pi r squared times gamma L minus gamma S, and we have 4 pi times r minus t squared times gamma SL. And this is kind of our part two. So now if we add this one to this one, we'll have an expression for the total free energy change, the bulk, plus the surface. So now let's do that. So our total delta G upon melting is equal to the bulk plus the surface. And here we're just copying what we have above. So we have it on this slide. We'll do it. And so now if we assume that we have this system where we're sitting in this state where we have a thin layer of liquid of thickness T around the particle. How could we tell mathematically whether it's favorable to melt the rest of the particle? So energetically, what would our criteria be for that? Can anyone suggest what we want to do next? Which way would the energy change need to go? Any ideas? Just a guess. Someone.
Negative.
Negative. Right. So the idea is that if we have a net decrease in the total free energy of the system, then it will be favorable for this T to go from whatever value it is now to the maximum value, which means it would completely consume the particle, and there we could consider that we're effectively in the molten state. And so how do we do this mathematically? We take a derivative, and we're basically going to find that if the first derivative, a delta G with thickness, is less than 0, then the particle will melt. So we just need to take the first derivative of this big expression up here, which looks kind of messy, but it's not quite as messy because if we're taking the first derivative with respect to thickness, we see that not everything depends on thickness here, so a lot of terms just go away. So for example, we're not going to worry about this term because there's no dependence on t, and we're not going to worry about this term. So both of those will immediately drop out of the derivative, and we start writing it out. We need the first derivative of this r minus t cubed, so let's bring out a negative 3, and then the prefactor all remains. And we have r minus t squared as our first term. And we also have the temperature differential. And then for the second term, we're going to get a 2 and a minus 2 because of the first derivative here. So we'll have negative 2 times 4 pi times r minus t times gamma SL. So, sorry, the second term here, we'll have a negative pop out of here. Yep. So where do you get the, so I agree about this one, but over here, if this is positive and we take first derivative r minus t, that should give us a negative, I think. So is that good? Okay. So now what we want to do is solve for the case where this is equal to 0. So if we solve for the case where this is equal to 0, we can start canceling. Well, the 3's cancel anyway. The 4 pi's will cancel. And then we will have the case that 2 gamma SL, and we can also cancel 1 of the r minus t, will equal h naught divided by the bulk melting point times r minus t times the difference between the bulk melting point and the temperature of interest. And if we solve this for t, then we'll get that the thickness is equal to r minus 2 times the bulk melting point times gamma SL divided by H naught times the temperature difference. And this is the thickness at which the melting would proceed from that particular thickness to a fully melted particle. So we're going to call this our critical thickness. And in a real case, we can't really imagine that we all of a sudden have this critical thickness of liquid, and then okay, we give ourselves this critical thickness of liquid, and then melting proceeds. So in order for melting to be spontaneous, to start from 0, the value of T has to be equal to 0. So basically, when T is equal to 0, then we can relate the melting temperature T to the radius of the particle r and things we know as constants, the bulk melting point, the surface energy, and the latent heat. So what we're looking at is a plot of the surface energy or the free energy change upon melting as a function of this thickness T, and that should be symmetric, sorry. And we have this critical thickness T sub C. And now this is the case where the free energy is at a maximum, and increasing the thickness equals a net decrease in the free energy. So then we say that the particle melts spontaneously if the critical thickness is 0. And then this tells us that at a given temperature, the corresponding particle radius is, just by rearranging what we had on the last slide, is this expression. And then we can rearrange terms, and we can say that the difference between the bulk melting point and the melting temperature is just equal to flipping this term up to the left side and bringing the radius down. And then we would get that our melting temperature, T sub m, is equal to the bulk melting point times a factor that relates to the surface energy, the latent heat, and the radius of the particle. So it's kind of like the melting point is equal to the bulk melting point times 1 minus some constant C divided by R. So there's a limitation to this. Like, it's not true that everything that's really, really small is a liquid at room temperature if you imagine an infinitely small R, but it gives us some, kind of qualitative insight that, the suppression in the melting point, or the value of the melting point of this small solid, is lower as the particle gets smaller, and therefore there's more surface available, there's more surface relative to the volume, and therefore it's more likely to melt. Also, the value of this term increases as the surface energy of the solid-liquid interface increases, and it decreases as the latent heat, or the heat required to melt the material, increases. So if the solid requires more heat to melt, then you're going to relatively have a lesser change in the melting point, or you're going to need to give it more temperature to reach the melting limit. And this is a fit from the paper that's in the readings from Couchman that uses this simple thermodynamic theory to relate the melting point predicted by the theory to data for indium. And I forget what the different circles and triangles here mean, but you can see that generally this decrease is observed, that as the in this case it's plotted versus the inverse radius, so this means smaller particles going to the right, and the temperature is decreasing from the bulk melting point to a much lower melting point as the particles get smaller. And notably, indium is a metal that melts at relatively low temperature anyway, so this is like 430 Kelvin, so that's about 150, 160 C. But this decrease can be pretty significant. So if we look at the value of this r to the minus 1, that's 0.02 inverse angstroms, so that's 50 angstroms, or 5 nanometers, right? So it says that at 5 nanometer particle of indium, it is going to melt at, say, 80 Kelvin beneath the bulk melting point, which is about a suppression of 20%. So it's a non-negligible decrease in the melting point, and is a much bigger decrease than, for example, we saw like in the lattice spacing due to the internal pressure inside the solid. And another important and practical aspect of melting point suppression relates to the synthesis of things like nanotubes and nanowires, or the migration of nanoparticles on surfaces. And so this similar computations can be done for pretty much any solid if you know the parameters that we had in our equation. And so this is just a plot from a paper that is talking about catalysts for growing nanotubes and nanowires. And here we're going up in diameter, and so it says that, for example, for these metals, iron, nickel, gold, and silver, beneath a size of, say, tens of nanometers, we start seeing a significant suppression in the melting point due to size. And where this comes into play is, for example, if you want to grow, say, carbon nanotube from a nanoparticle of iron, or a silicon nanowire from a nanoparticle of gold, the rule that we'll talk about later is that roughly the diameter of the particle is approximately equal to the diameter of the nanotube. So say I want to grow a 5 nanometer diameter carbon nanotube, so I want to have a 5 nanometer diameter particle of iron. And a lot of the processes that make carbon nanotubes are thermal processes, so you heat the particle and you bring it in a high temperature hydrocarbon atmosphere, and you're trying to get carbon to dissolve on the surface and inside the iron particle. So that particle, even though at say 1000 C or 800 C, it would be still solid if it were a bulk, is going to quite possibly be liquid at this temperature. And the same thing occurs for gold at temperatures that, for example, would grow silicon nanowires of that size. So this ends up being a pretty important consideration and relates to a lot of other things, like the diffusion of the reactants and the mobility of the particle, and also even before a nanoparticle becomes liquid, because of the greater mobility of the surface atoms, it can actually change shape and still remain solid. You might remember the picture, the video I think we had on the first day, where this was an in situ TEM video of a carbon nanotube growing from a nickel particle. And we didn't talk about melting point suppression, but this was at about 500 C, and the metal particle was actually kind of inching along like a worm. It was changing shape. It was kind of squeezed out and then jumped forward. And it's not clear if this was entirely liquid at that state, but certainly it was compliant and could change its shape at about a temperature of 500 or 600 C. So if we look at the case of nickel here, I don't have a length scale, but I think this was between 5 and 10 nanometers. So between 5 and 10 nanometers, nickel is melting in a range of, say, 600 to 1000 C. So it's quite possible that this particle may have been liquid under these conditions. And also, the atmosphere is going to make a difference. For example, whether you have hydrogen on the surface or something else on the surface can modify the surface energy, and therefore can change the values of the parameters that we have in our equation, and therefore change the practical value of the melting point. But the thing I want to go home with today is to just realize that there is this significant suppression, and that it depends on the bulk characteristics of the solid and its size, and can also depend on the environment. So there's been more work on watching materials melt, at the nanoscale. And for example, I think this is a picture from the second paper that you'll be reading. Here they're looking in a TEM, and they have a film or a bunch of quantum dots. And here, this is a lattice resolved image of an individual quantum dot. So in this case, it was a cadmium selenide crystal. And they heat them, and they melt, and they cool them, and they kind of form a polycrystalline film. And they see that the order, this is a line scan of the electron diffraction pattern, the order of the crystal increases after the dots have been heated and cooled. And they study, for example, the question is, well, how do you determine that the particle has melted? Well, in the case of going from a solid to a liquid, if you're looking at, for example, the diffraction pattern, then the strong diffraction peaks that correspond to the order of the lattice would go away when the particle goes from solid to liquid. So if you plot, for example, the in arbitrary but the same units for each particle size, the intensity of a certain diffraction peak versus temperature, then you'll see that when that intensity drops way down, basically when the atoms are no longer ordered to cause the diffraction of electrons, then the particle has melted. So what they do is they look at the temperature at which the diffraction intensity decays for different particle sizes. And this represents small particles going up to larger particles. I think they have, for example, 12 angstroms or 1.2 nanometers, 1.3, 1.6, 1.8. Those are radius values. And as predicted, you could say by the theory, the melting point increases with size. And then they plot some more data over here where they just take basically these threshold temperatures and put them on a plot, and they compare it to the simple 1 over R theory that relates the melting point suppression to the size. And there's some interesting discussion in the paper that talks about the difference in the melting behavior of crystals that are capped with an acid molecule, a stabilizer that was used in the synthesis and not. And they, for example, see differences in the melting point of the particles based on what's on the surface. And the details aren't important for us, but as you can imagine, the molecule on the surface is changing the stability and therefore changing the melting point. And maybe if you heated it up once and you burned off that organic coating and then you cooled it down, then maybe its melting point on a subsequent heating would be the same as the particle that had not been coated with that molecule. And there's also a connection to what we saw back in the early days where we talked about magic numbers. Remember that because of things, physical structures, very small nanoparticles, clusters being, quote, geometrically closed, we saw that the ones that were geometrically closed were more preferential. So this is a plot like we saw before. I think these are of sodium clusters that were made by evaporating sodium in a beam and then doing taking a mass spectrum, so basically counting the relative intensity of a certain size, and these represent the magic number clusters. So you see clusters of all sizes, but you see relatively more of these particular sizes. And then they did studies of the melting point of these different clusters, and in fact found that the structures that are closed, that are more stable, have a higher melting temperature than the ones that are less stable. And just from a purely qualitative point of view, we can now kind of imagine why that's true, because the energy change needed to melt a cluster which is less stable due to its configuration of atoms would be lesser than one that is more stable. And there is, a connection between this and what we saw at the beginning of the lecture with respect to the geometry. But, in practice, there are not a lot of applications or abilities to make, large quantities of atomically precise clusters, or, for example, to take advantage of, say, differences in their melting points. I think this is an interesting, analytical or theoretical point. But in practice, it's just important for us to see that the melting point decreases due to these surface effects, and that can have a profound effect on processing and synthesis. It can also, for example, mean that you can convert a bunch of nanoparticles into a solid at a much lower temperature than you would, say, melt that bulk solid. So there are implications for bulk materials processing as well. So there are a number of ways that this melting point analysis could be done, and the papers might talk about different ways and reference ways that, for example, consider that the density of the solid and the density of the liquid are slightly different. And those different models might get slightly different results, but they would end up with the same trend. And in general, all of the models that take this simple thermodynamic approach will get the final result that the temperature of melting is equal to the temperature of melting of the bulk times 1 minus some constant divided by the radius. And another kind of simple qualitative way we could have looked at this problem is to kind of think about the stability of our lattice in terms of the total energy of the system, or the average energy per atom. And basically the idea here is that if you have a bulk material, then you can say that each atom has a certain cohesive energy, a sort of certain bonding energy. And if you have a smaller material, then you're going to have to, even in the bulk material, you have to subtract some energy due to the surface, like we did at the beginning of the lecture today. But if you have a much smaller material, then the surface becomes more important. So the total energy of this solid per atom is going to decrease more because you have more surface, and you're going to have to subtract more of a contribution due to the surface per atom. So if we defined what's called the bulk energy of a solid, we could say that it equals some energy per atom times n, which is the number of atoms. And if we wanted to consider the surface, we would subtract the surface area multiplied by the surface energy. And if we then just divide it by n, we would get our bulk cohesive energy per atom minus the surface energy, or the surface area, times the surface energy divided by the number of atoms. And we're going to call this A sub v, comma, nano, which I just mean it's kind of a correction to this bulk energy due to surface effects. And if we ran this out for a sphere, which I'll call NP, so a nanoparticle, we would get that this equals this bulk value minus 6 times the surface energy gamma times V sub A, which is just an atomic volume divided by the diameter of the sphere. So we've just recovered a surface area to volume ratio, kind of like what we derived on at the beginning of lecture 1. And I'm doing this because through another relationship between the melting point and the bulk energy of a solid, basically how strongly bonded the atoms are together is directly correlated to the melting point. We could then say, well, if the fact that our material is nano-sized results in a suppression of this average bonding energy, like averaging over all atoms in our small solid, thinking of them all in an average sense at this point, we can then relate that to the surface area to volume ratio of our structure. And by this approach, the details of how I get to what I'm going to write next aren't important for us, but we could get, for example, that the ratio of the melting point of the nanostructure divided by the bulk melting point is equal to 1 minus some parameter beta times the surface area to volume ratio. And this beta will depend on the material properties. And if we did this simple exercise and we don't need to go through all the geometries, but if we did this exercise and we derived the surface area volume ratio for a sphere, we would get 6 over d as we did before. And if we did it for, say, a nanowire, we would get that the surface area to volume, if we have a length of L and, say, a diameter of d, is equal to 4 over d plus 2 over L. And if L is much greater than d, then we would get that this is just equal to 4 over d. And if we did it for a thin film, where we had, say, to keep the same parameter, we had a thickness d and we had, say, a lateral length scale L, then we'd get the surface area to volume if L is much less than d is equal to 2 over, d. Where here d is our film thickness. So by this kind of dimensionality, you can see that the amount of suppression of the melting point will be relatively less if we increase the sort of dimensionality of our system. So in this ratio of kind of like 3 to 2 to 1, 6 over d, 4 over d, 2 over d, the melting point suppression of a sphere versus a wire versus a plate would be correspondingly less, and a plate would melt at a temperature that's closer to the bulk melting point than, say, a nanoparticle of the same diameter as the film thickness. So just to lay out formally, if we said T, the bulk melting point minus the nanoscale melting point divided by the bulk melting point goes as 3 to 2 to 1 for a sphere versus a wire versus a film. And there's been some work, for example, to computationally study how melting point depends on shape. And you can, for example, see that the trends that are retrieved for wires versus spheres of different radius, so large to small, bulk to nanoscale, are different. And Here it says the solid circles refer to wires, the squares refer to clusters, and the dashed lines are the prediction of the theory, and the squares are results from molecular dynamics simulations that compute the melting point as a function of size. So this, while the agreement may not be exact, this idea of, because there's less relative surface, wires being more stable than spheres certainly has an important effect as well. Okay, I think that's where I should stop for today, and we'll talk a bit about the last topic, wetting, when we pick up next time. Are there any questions?